Okay, thank you everyone. My name is Xingkai and from Niantic. I believe a lot of people know who we are, right? Welcome. Yeah. And yeah, talking about Pokemon Go, I think probably a lot of people still remember at the first summer we launched Pokemon Go. It's super popular, and we are happy for that. But we got, most of you probably also remember how kind of we have the, like the service is not that reliable because we have a lot of customers. It's a good problem to have. We are so proud of that, but also we are so embarrassing at the same time. So think about it. So I just want to share mention about that because I want you to have some understanding what is the problem we are facing. Think about when we have 5 million customers playing Pokemon Go at the same time, and every one of them kind of have a query to our server every other 5 seconds. If in that scenario, we are talking about 1 million QPS. That's a scale we are talking about. A lot of time when you develop a service, you are happy when you play with it, when you are testing it. But when a lot of customers come in, that can become different. So this is WStore is a code name. We create our database to kind of handle large volume queries. And to be honest, this conference HTAP, right? So I want to explain something about WStore to help you understand what kind of database it is. Think about a database solution as a whole spectrum. Some of the database is very simple, like a TiKV store. For example, TiKV store is like here. It can store very simple data, like a key is a beta array, value is a beta array, and it don't have structure by itself, right? A more advanced database is something like here. It's more like a SQL database. Or, for example, TiDB is also kind of more or less like a database. It can store things. It's more like, typically, it's more like a raw-based database, right? It's a support transaction. It can save things, read things. And more advanced database, sometimes we don't call it a database. Sometimes we call it a HTAP, right? It's, for example, if it's a TiDB plus a TAP flash, then you run into basically a raw database plus a column database that you can do a query, like all kinds of queries very, very fast in large scale, a data lake, right? So if you look at WStore, you will see WStore stays somewhere between the SQL database and the TiKV store. The reason for that is we need to handle huge volumes. And we don't need those kind of fancy join operation or fancy query that we have some other like data scientists or data flow to handle those things. Here, the only problems we need to handle is like when huge number of customers all come in to try to catch Pokemon or try to spin a Pokestop, we need to respond. We need to kind of save their inventory and respond them in a meaningful fashion, right? So that's why we need something more complicated than a TiKV store because we need index. We need support some kind of query, and also we need a transaction. So that's why we are somewhere between a TiKV store and a real database. So that's what we do. So internally, the WStore is a database as a service. It's a gRPC service. It's not really a SQL or SQL compatible. It's by design. We don't want to create a SQL. And as I said, the WStore is a trade-off between scalability, feature set, and complexity and cost. And in terms of, yeah, the way how we achieve scalability is like the WStore is designed in a way it's stateless by itself, and it's work on the TiKV cluster, and it becomes kind of have a good scalability. By the way, TiKV is made by PingCAP, and the TiDB is based on it. So we are not using TiDB directly, but we are using the TiKV. And thanks for PingCAP. By the way, officially we are we are using community version of TiKV, and thank you for you to kind of helping us. And yeah, the feature we implement is a subset of a real database. We need an optimistic log-based transaction. We need transaction, but we don't need a pessimistic log transaction. That's too heavy for most of our applications. And we need a nice index, like multi-column index. We implement a zigzag merge join, those things. And in terms of complexity, as I said, we kind of intentionally don't want to go too far to on a real SQL database side. We want to make a trade-off. So it's a very simple design, stateless, and does not support join. And yeah, our solution is based on the open source software stack, like the gRPC, TiKV, Golang. Yeah, Golang is my favorite. Yeah, this is a very sophisticated structure, right? TiKV cluster is here. We have a lot of them. And WStore is in the middle. It's stateless. So when we have a lot of traffic, we can spin up more, and they can all handle traffic in the same way. And the client side is our customer of the game server need to read and write. That's pretty much about this. If you look at the structure, you will notice actually WStore is very, it works kind of similar to like TiDB in a lot of ways, but it's just our customized, a simplified version of the TiDB. Yeah, that's a good question. I simplified this a little bit. Actually, we do depend on PD, because TiKV cluster need PD to work. So it's we use them as a whole thing.
Okay, but do you use PD for your transactions?
Yes. Yes. Yeah. Sure.
Can you say a little bit about what was the motivation for building your own and not just use TiDB?
Yeah, that's a good point.
Honestly, its feature set is a superset of what you need.
Yeah. Actually, that's a very good question. Internally, we have that discussion for a long time, and also still, even today, a lot of people still asking. I think it's you can see pros and cons in different choice, different design decisions. But what we are thinking is, since we are facing the scale that we are not many people is really facing, and so I think we are worried about if we choose a full-fledged database, unless we do an extensive load test and make sure all their queries are all kind of, yeah, it's a possibility. It's a better choice, but sometimes we just the scalability is one concern. Another concern is we think if we build this, it's a simplified version. So potentially it can save some resource, computational resource, because we don't need to build the SQL parser. We just use the gRPC, and it's heavily customized for our application. And also it's if we have some scalability issues, we have more controls on how do we solve it and what is the problem.
Do you have some sense of how much cost you would have saved by going this route versus using TiDB in a restricted fashion?
Let's hold on to the question until we get the mic. These are good. We want to get them recorded.
Do you have some sense for how much cost you might have saved by going this route versus just trying to use TiDB in a restricted fashion?
I think That's, we did a lot of load tests. And well, cost is one thing. Another thing is the scalability. We need to make sure it can support like 1 million QPS. And, and also we want to have more controls when things go really large. That's another consideration, basically. In terms of query per second, performance test result number, we did a lot of tests, and but I don't think I will share you those concrete numbers because everything is evolving, and the PingCAP is also keep kind of implementing and polishing their performance.
Right. If you can share a little bit on how you convinced yourself that IDB won't scale, which component turned out to be bottleneck for you, that would be great to share.
I think that's the purpose of today's sharing. Yeah, I'm not saying our system is perfect. I just want to say we make that choice at that time, and I want to show you some of the learnings and fun stuff we get along the way. Yeah, but thanks for asking those. Those are good questions. So yeah, WStore is the API of WStore. As I said, it's a gRPC. So if you look at the API, it's very simple. It's more like geared towards the simple web service style instead of a SQL style. The first, most basic API we have is GET, right? GET is just a get one entity from database. And in the GET request, you have the table name, and you have the key. And in the response, of course, you have the payload, right? That's a GET. And the put is very straightforward, right? It's a put is put the entity. It's a batch put, actually. It's you can have a list of entity, and after we write it, we respond. And we support search. Search pretty much means you can have searching criteria. You can search based on the primary key, and also you can search based on the indexes, because each entity may have some properties. You can do a search based on properties. Because underlying, we make 10 indexes for those entities. So just now I talk about entity. So you can think of entity like it have key. For example, we are using a player table. So the kind is basically the table name. This is a player table. And this ID is entities, this table, this entity's primary key. And every entity may have optional property list. In this entity, player entity, it have a nickname. It have a string value, and it's indexed. And an entity also have a main payload. In our case, the payload is always a beta array, and it's actually a protobuf. So that's the data we actually all the game is depending on. So as you can see, this entity is only thing our database need to handle. It's not a real that fancy stuff, but it simply works, and also it's proven to be works under scale. Sure.
But yeah, I mean, so I told the hiring manager 7 months ago.
Are you storing only entities, or are you also storing edges between entities?
That's a good question. We store only entity. Yeah. So we do not support join operation. If you really want something like that, you need to have those in your property and mark that property as indexed true. So yeah, you see, it's a simplified version. That's why I want to mention it in the early stage. We are somewhere between the real database versus a KV store. Yeah, this is a little bit details. I'm not sure whether it's entertaining to everyone. in order to store the entity just now I mentioned, and we store things based on the KV store, right? We don't want to deal with the kind of file system by ourselves. So we store everything based on KV store. Our WStore is based on KV store, TiKV. So the data is stored in this kind of KV pair. The key is like have the kind, which is table name, and the row ID is the row ID because it's, and the value is just the payload, the protobuf payload, basically. And we need a primary key index for this record, right? So basically, the primary key index is the same. The key is include the table name, index ID, and index value. Well, I think in this case, index ID is always fixed because it's a primary key. And index value is basically the ID 007 thingy because that's what index is. And the value is just row ID because when you want to read things from based on the primary key, you look at this one first, you look up this index first and find out row ID. And based on row ID, you can construct the key to load the payload out. That's how things works. And we also support like a regular index. Regular index is very similar to primary index. Just it's have the yeah, it's just the index ID is not the default one. It's just some key, and when you read it, it's the same thing happening. So in order to save just now the entity, you need these three. I mean, eventually, what write into the TiKV are those three key value pairs. That's about it. Yes, we do. So I simplify a little bit here. So the reality is here, there's optional field. If you want support unique constraint, you don't have anything above this. If your index is non-unique, you need to do an underscore and put a row ID here after this as a key, right? So you can do a search because in TiKV you can easily do prefix search, range search, those stuff. As long as you can construct the prefix, you can scan it whatever you want.
Okay. Yeah. Remember.
Any question?
Okay. Okay. Just to the lady.
Okay.
You is that?
Yeah. So I think that's. I don't want to go too deep on the implementation details. I want to show some learnings. We kind of. It's fun. Yeah, first, when we talk about the how to evaluate those system performance, we do a lot of load tests, and for obvious reasons, that's important for us. So the way we do load test is just like the axle is pretty much how many client-side thread we are using. And basically for each thread is a tight loop. We kind of bombard the server with as fast as we can, right? So the output is a QPS, right? This load test, actually this graph itself, I don't think it's come from a real TiKV load test result. I just grabbed this one randomly to show what the graph looks like. So a lot of time we are interested into those, where is the top, the maximum out, the QPS looks like, because that represents what's the system kind of maximum capacity when it's saturated. It's that number. That won't change if you. That number is more reproducible because sometimes you deploy your client on a little bit different rack or different data center, the client-side latency may change, but that saturated QPS number will not change. And other than that, sometimes we will also look at the 100 millisecond latency. When that happens, what the QPS looks like.
So how is that related to HTAP?
When we do load test, we find some interesting kind of behavior, which is when we do compared to read versus write, we notice the write is pretty much 10 times more expensive than read if the payload size is on a similar scale. So I remember a long time in my previous life when I'm using the DemoDB, I remember that when you provision in the bandwidth, right, the write is 10 times more expensive than read. And here, I think my load test result here is also kind of suggesting similar things. I think there's a few reasons behind it. One of the reasons is like when you read things, think about it. You have 3 replicas. You can hit any of the replica and get the data out. You're happy. But when you write, you need to, the data eventually going to hit all 3 replicas and all kind of flush to the drive and make sure they all write successful. And sometime when you use the cloud drive, and each cloud drive, cloud disk also have 3 replicas. So it's kind of expensive in nature. So that's one findings we got.
And then they have like, each script is like 5,000.
And yeah, QPS versus payload size. We noticed, yeah, for example, when we have a cluster which use 8-core machine, 100 8-core machine, I'm talking about TiKV cluster. When you use a very small payload, so how should I put this? So think about the QPS will be subject to payload size. You can easily kind of think of when the payload is large, the QPS you get probably going to be slower, right? Going to be lower. When you have small payload, the QPS is likely to be larger, until you run into some tipping point where the QPS will become maxed out for some other bottleneck other than the bandwidth usage. The image here I want to show you is when the payload size is large. For example, when you're writing some like 100K or even half megabytes payload in the write request, probably you are going to run into some bottleneck caused by the disk bandwidth, network bandwidth, or some sort of bandwidth critical resource. But if you're running some load test based on very small payload, maybe 10 bits or 100 bits, probably you're going to run into some bottleneck, more like CPU usage bottleneck. So, for example, we did some small load test, the small payload load test. For example, both of them is we see the QPS is almost like 400K QPS. Despite the payload size, because payload size is small enough. But if we try the other extreme, which is the payload size is pretty large, and it becomes, the QPMs becomes kind of lower when the payload size increase, but the total bandwidth, kind of the write throughput becomes capped out, becomes maxed out. So that's a thing we observed, basically. And I think that's fair, in my opinion. Any comments or questions? Yeah, and like I mentioned just now, when the payload size is small, the system can handle high QPS, but and the bottleneck is pretty much the CPU bounded. The TiKV CPU get capped, get maxed out. And when payload is large, most likely you will run into some sort of bandwidth bound. And in our experiment, I believe the result is showing the disk I/O bandwidth becomes a critical resource. And at that time, when that happens, the CPU, if you look at CPU usage, memory usage, they are all pretty low, relatively low. And Yeah, so the thing we care most, we worry about most is how scale the TiKV can support. For example, 500 nodes, 1,000 nodes. Does it can really scale up to 1 million QPS? So we did a lot of tests on it. So the result is, the conclusion we get is pretty much, it's a good news, I think. The TiKV do scale when we add more nodes. Until you run into some bottleneck. For example, when our experiment, the maximum number I said here is 300 nodes. When we tested beyond that, we start running into the PD CPU kind of bottleneck, because when we have a lot of TiKV nodes, the PD, we notice that we have 3 PD instances, but only one of them CPU is high, and the other 2 is basically just hot standby, it looks like, at that time. I think they improved this part in the later kind of release. But that's what we got last time we tried this. And another problem you can make the TiKV don't scale is if you don't, you want to make sure you don't have hot shard. I will revisit this one later, give you some more example on what hot shard looks like. Another interesting question we want to find out answer is like, look at those A and B setup. We want to find out what is the best optimal kind of setup we want to use. What is the most cost-effective setup we want to use? For example, setup A is we have like 32 core machines. And the setup B is we have 128 8-core machines. And if you look at those 2 setups, you do your calculation, you will find out the cloud provider, the quote they give you is the 32-core machine is pretty much the 4 times the cost as the 8-core machines. So our question is, which one is a better choice, or some other configuration is even better than those 2 choices? So basically, we want to have some understanding on what kind of setup is better. We want a large number of smaller machines or smaller number of larger machines. So what do you guys think on those 2 setups? Which one can give us better overall throughput?
B?
Yeah, how many? Oh, you said PD, when PD is a bottleneck, then those 2 should be the same, right?
Sorry. If PD is your bottleneck, then I would guess you would get better throughput with setup A than setup B. If PD is your bottleneck.
Yeah, I think you're right. If PD is a bottleneck, then the PD's machine size will be the bottleneck. That's a little bit different topic. When I talk about the comparison here, I'm actually talking about have a very big free machine on PD and make sure PD is not a bottleneck. And just look at the TiKV support. What are which setup, which cluster can give us better overall throughput? Assume PD is not a bottleneck.
Then I would guess cluster B.
You guess cluster B. So does anybody else guess cluster B? I see some people raise their hand. Does anyone guess A is better? Okay, I see a fair amount of hands as well. Yeah, that's interesting, right? Because if you look at the price, they are the same, right? So the answer is B is better. So do you want to share why you think B is better?
Effectively, you're distributing the load over more machines, assuming you don't have too many hard shards.
Yeah.
So with each machine, you have a separate set of bottlenecks for both disk and network bandwidth. So if again, you're running into any kind of bottlenecks, usually by distributing over more machines, you end up with a better state.
Yeah, that's a very good point. So we take some time to look into those things more. Compared to the smaller machine, because as I said, we are testing like 4K payload size, which is kind of on the larger side. It's not bottlenecked by CPU usage very often. It's more like bottlenecked by the bandwidth. To be more specific, by the disk I/O bandwidth. So when you look at the machine specs, 8-core machine, IOPS, it's like 15K, and the bandwidth is 400. If you look at the 32-core machine, it's better, of course, but it's not linear. This bandwidth is kind of more than 1/4 of this. And another thing you need to pay attention is disk also have bandwidth limit. The 500 giga cloud SSD have those numbers, and the 2T is better than that one because disk bandwidth is also kind of like depend on the disk size. The price is 4 times, but if you look at the bandwidth, this one is more than 1/4 of the large disk. It's not really linear, especially when we talk about when you use a 500 giga disk with an 8-core machine, it will take the 200 megabits per second as a real bottleneck. And when you're using this one, the beefier machine, but using this disk, the bottleneck will be this number. So that's basically what we get. That's our learning. So the idea is since the bottleneck is the bandwidth, and also another thing worth mentioning is this IOPS, in our measurement, in our dashboard, TiKV. Oh, OK. So in the TiKV dashboard, it's we are not IOPS bounded because TiKV is a kind of journal-like system. It's heavily batching, so the bandwidth matters, and IOPS don't matter that much. Any questions?
So, do you have actually numbers on UPS versus to setups?
I do have numbers, but I don't want to. But some of the tests is done like a few months or half a year ago. So I think TiKV continues doing improvement. I don't want to show those concrete numbers. I just want to share the trends and the conclusions.
Relative numbers like B like 20% better than A.
Oh, I see. It's not that huge difference. It's like 30% or something like that. Let me see how many do I have. Oh, I see. I don't have enough time, so. Yeah, I want to mention something about hot shard problem. The one learning we have is when we use the row ID, previously we have a monotonically increasing row ID, but when we do that, we easily run into hot shard because all those key values will be run into the similar shards. So the solution is we need to shuffle row ID. And another learning is when we previously we have some index value is using timestamp, and that will also create hot shard. The solution is we need to add some salt before the timestamp. Otherwise, you will not, your write QPS probably won't go too far until you hit this problem. When that happens, what you will see is out of 100 TiKV nodes, only 3 of them, the CPU usage or the bandwidth usage is maxed out, and all others are just idle, cannot help. Thank you. Oh, OK. Any questions?
Okay, thank you. That was a great presentation. So one question I had is for the TiKV client, are you using the raw API or the transactional KV API?
We are using the transactional API, the optimist log transaction.
Okay, so which means that if you get a single write, you have to write the main key value and then the index entries. So do you do that as part of the same transaction?
Yes. We normally our typical use pattern is write after read. We read first, and then we write. When we write, we use the transaction, the read timestamp, and we also use read log to make sure nobody else ever touched those data, because that's the data we depend on to make decision. And when we write, if we can write successfully, that means nobody else is touching those data, and we conclude this transaction.
Okay. Thank you.
Thank you.
I have a question. Hi, great talk, by the way. Thank you. So what is typical, your read-write ratio typically for your normal load?
That's a good question. So as I said, a lot of our application is using reading the inventory and then add or remove some item into it and write it back, right? That's one of the typical workload. So for this kind of workload is almost one-to-one.
Oh, wow.
Yeah.
Okay. All right, thank you. Any other questions? All right.
Thank you.
Thank you very much.